We're going to talk a little bit about quadratics today. And if you were struggling with homework number 1, what we do today might help you because we're going to see transformations with a specific type of function. So in your foldable, you have your 8 doors or windows or whatever you want to call them. Okay. The top 2 are going to be for absolute value function and greatest integer function, and we're going to fill those in during another day to review what the transformations look like there and put the parent function. So on this door right here, second door on the left-hand side, what we're going to do is we're going to write the title quadratic function, write the parent function equation, and put the little graph of it. Okay? So it's going to say quadratic function. It's going to have the parent function equation, which is y equals x squared. That's what makes quadratics the squared part of it. And then we're going to draw a little graph of the parent function. So in the end, we want all the parent functions memorized. We want to know how they work. Okay? How you could get a parent function, you can plug in points. Okay? So if I plug in 0 here, I get 0. So let's see. Here's my x-axis. Here's my y-axis. So my 0, 0 is right here. You guys can just sketch it like an x and y axis. There's 0, 0. What do you get when you plug 1 into the function? 1. Okay. So 1, 1. What about when we plug in negative 1? 1. Okay. So far it doesn't look much different than absolute value. But what makes the function curve is what happens when you plug in another number. In absolute value, if we plugged in 2, we would just get 2. Every time we moved 1 further, we went 1 up. Here, when you move 1 unit away from the vertex, you went up 1. But when we move 2 units away from the vertex, in other words, when we plug in 2, what do we get? 4. This is what makes it look curved instead of like straight lines, right? It starts growing at a different rate each time because you're squaring the numbers. So when we plug in 2, we get 4. And when we plug in negative 2, we also get 4. Okay? And then this would continue. When we plug in 3, we'll get 9. Negative 3 will also get 9. Okay? All right, so that's all I want on the front door. Okay? You have it labeled as quadratic function. You have the parent function, and you have what those points are. What you need to know is that a quadratic function looks like a parabola. Its vertex is at 0, 0, and when I go 1 away, I go 1 up. But when I go 2 away from the vertex, the difference is now 4. Okay? That's what we're going to be using today. Right, so we're going to use this information today, the parent function, to walk through transformations. All right? That's the only thing you need on your note guide. If you're going to need the parent function later, like you don't remember this, some of you are really good with quadratics from Algebra 1, some of you aren't, then you can keep it out on your desk. Okay? All right, and then in the note guide, I want us to look at example 1. Sorry, let me move it down. And we're going to graph this. It's written in vertex form, like we discussed yesterday. And then what we're going to do is we're going to graph it by using the transformations. Okay, so the first thing we want to do is we want to look at how the parent function has been changed. So the parent function is what we just graphed, x squared. Okay? The things that are different here from x squared are this 3, this 5, and this 1/2. Okay? So then based on our conversation yesterday about transformations, what differences are those numbers, what impact are they going to have on the way that the graph looks? Okay? So this 3 right here, what is that going to do to our graph? Savannah? Okay, good. So we have a translation. There's a spot at the bottom that asks you guys if you have the note guide, write it underneath the graph to list all the transformations. If I do that, you won't be able to see, so I'm listing them right here, okay? So we have translations. We have one that's to the right 3. What is our other translation that's going to happen? Good. We're going to go down 5. So that's going to take that entire parent function parabola and shift the whole thing to the right 3 and down 5. If there was nothing else, we would literally take the picture you drew as the parent function, move everything over to the right 3 and down 5, and we'd be done. Okay? But there's another transformation happening here. What is the 1/2 doing to our graph? Michelle? Good. Okay? And is it a vertical or a horizontal change? vertical. It's outside of the function, right? So this is vertical, and it's a compression because with vertical, what you see is what you get, right? Basically, all of our vertical distances are going to get multiplied by a half. So we have a vertical compression. And then for myself, you guys might not like this, but for myself and for the value of explanation while we're taking notes and stuff, I like to literally write all the distances are being multiplied by 1/2. So that's just my little times things by 1/2 when you're looking at the vertical distance. So what I'm going to do, because we haven't done a lot of transformations yet, so I won't do this all the time, okay? But I'm going to put up here in a really light color, like yellow, what the parent function would have looked like, and then talk about how we can quickly get our new graph knowing these transformations, okay? So remember, my parent function would have this point at 0, 0. 1 away would be 1 up, and 2 away would be 4 up, okay? So this is not the graph that they are asking me to graph. This is the parent function that this graph comes from. Oops. It belongs to this family of parabolas, okay? So I'm just thinking about how those are structured and how they work. Here's how I would make the changes based on what I see here. If I'm translating right 3 and down 5, then my vertex will no longer be at 0, 0. It will be 3 to the right of that and 5 down from it. So it's going to be at the point 3, negative 5. Okay? So 1, 2, 3, 1, 2, 3, 4, 5. There's my vertex. Okay? Now, as I go to fill the points in around the vertex, I'm not going to follow the same exact pattern that I followed before, but I'm going to use that pattern and adjust it based on the fact that we had a vertical compression. So the vertical compression will only affect vertical distances of points from the vertex. Did everybody hear what I said right there? Okay, so a vertical compression is going to affect the vertical distance between the points we're going to graph now and the vertex that we've plotted, okay? Not the horizontal distance. So in the parent function, I went 1 to the right to get my next point. I'm still going to do that with this function because nothing horizontally has been affected. Okay? What has been affected is the vertical distance. So when we plotted this point in the parent function, we went 1 to the right, and then we went a vertical distance of 1 above the vertex. Okay? So we went a distance of 1 above the vertex originally. That vertical distance between the vertex and the point I am now trying to plot is what is being affected by this 1/2 compression. So that distance is getting multiplied by a half, and 1 times a half is a half. That means when I want to redraw this point on my new graph, I'm still going to draw a point that's 1 unit away from the vertex horizontally. However, is it going to be 1 unit above the vertex vertically? No, the new distance because of this compression has been changed to 1/2 unit above the vertex. So I'm still going to go 1 over, but I'm going to draw the point so that it's only 1/2 unit above the vertex. And that's going to hold true for the left side as well, because 1 unit away to the left also went up 1. When that's multiplied by 1/2, it'll now be a 1/2. Okay? So think about what we did in the parent function to get our point that was 2 units away from the vertex. We moved 2 units away horizontally. That's not going to change because there is no horizontal compression or stretch. And that point that was 2 units away from the vertex horizontally was a distance of 4 units above the vertex. Does that make sense to everybody? So originally, if I was graphing this, my next point 2 units away from the vertex would be 4 units vertically above it. But that 4, again, is getting affected by this 1/2 vertical compression. When 4 gets multiplied by 1/2, it's going to be 2. That tells me those points that used to be 4 units away from the vertex vertically now are going to be drawn so that they're only 2 units away from the vertex vertically. Okay? So every place in my parent function where I had a point, like this one and like this one, that were 4 units above the vertex, now their vertical distance is going to get changed so that it's only 2 units above the vertex. So when I go 2 away horizontally, I'm only going to go 2 units above the vertex. And same thing here. So now my parabola looks like this. So is this clear to everybody how we take the parent function? It gives us shape, and it gives us some exact horizontal and vertical distances. We move it, and then we do any reflections, compressions, and stretches that we have to do based on that new location. Is that okay with everyone? So I don't have to plug in any points to this. I totally have my graph just based on knowing what these numbers did to the parent function and knowing the very basic parent function shape. Okay? All right, so then we can answer these questions. What is our vertex, Lauren? 3, -5. All right, what is our axis of symmetry, Savannah? Good, way to say x equals. All right, now here's a little bit of something that's in here basically for your pre-calc life ahead of you, okay? When they ask for the minimum point, you get to list a point. So what is our minimum point? 3, -5, same as our vertex, right? The vertex of our parabola is always a maximum or a minimum, depending on which way it's facing. So the minimum point is the point 3, -5. But you have to be really careful as you move forward in your math career. When they ask what the minimum value is of the function, that is like, what is the lowest value that it actually reaches? This is not asking you for the point anymore. This is asking you for like the output. What was that lowest number that it reached? So they're only asking you for the y-coordinate. So this would be -5, okay? And that minimum value of -5 occurred at a position of 3 on the x-axis. So again, we used to just do this part, and then you guys would get to pre-calc, and it would be like you would be answering these all wrong. You'd just be like putting the whole point. So we just put this language in here to kind of get it in your head now, so that in your future path, that helps you, and it's already kind of wired in there, okay? All right, the domain. What is the domain of this graph? Michelle? Good, all real numbers, okay? There are no restrictions to the left and to the right. You can pick a point on the x-axis. You could find a point eventually that's on your parabola for that x value, okay? What about the range of our graph? I see someone. Yeah, Brooke. Good. So as far as the domains of the parabolas, as long as they're up and down, these are the only kind we're talking about right now, are always going to be all real numbers, right? Eventually they'll reach those x values. But the range is always going to be limited because the graph turns around somewhere. So you have some point where you turned around and your whole graph is either above that or your whole graph is below that, just like the absolute value functions, okay? Which means domain would always be all real numbers, but the range is always going to be limited. And in this case, y is greater than or equal to -5. Okay? All right, any questions on this problem? So how did we know where to put the vertex? How we calculated the distances of the other points and why they changed from the parent function. Are we okay with all of those ideas? All right, so let's do one more. All right, why don't you guys go ahead and give this problem a try. So we want, what are all of the transformations? We want you to be able to graph it. We want the vertex, the axis of symmetry, the minimum point, and then the minimum value and where it occurs at. And actually, in this case, it should be a maximum. Does everybody know why I'm saying that? Yeah, it faces downward. Okay, which is going to be what kind of transformation? How are you going to list that in your transformations? Good, either reflection over the x-axis or vertical reflection. You guys can use either of those words. But we should change this to maximum. Okay. All right, so go ahead and try it. You can work with the people in your group if you're stuck. All right, so let's take a look. So our transformations. What were our translations? Okay, what were our translations? Zach. Good. So left 5 and up 2. Okay. Do we have any reflections? Yes. Okay, because we're multiplying by a negative. So how would we label this reflection? I see Savannah and Lauren. I totally appreciate them, but they've given me a lot of answers today. Samantha. Good. So you're either going to call it a reflection over the x-axis Or that means you could have called it a vertical reflection, okay, which means you're flipping things from above to below or below to above, okay? All right. Do we have any stretches or compressions? Andrew? Good. Okay, so it's vertical because the 3, and I'm talking about this 3 right here, okay, is outside of the function. It's a stretch because remember with the vertical number outside the function, you literally multiply by the number that you see, right? So when you start multiplying distances by 3, are those distances going to get longer or shorter? Longer. So that's why you're stretching it vertically, okay? So again, I know a lot of you are at a place where you're understanding more, but to be thorough, right, because some people aren't there, I'm going to show you guys how I would think about this and walk through the steps. So I have my parent function. And again, how do I know the parent function? I have memorized it. Okay, so there's my parent function. So as I walk through these different things, if you're going to do them in order, you should do reflections before you do anything else, okay? But if you understand how a reflection works, you can still do what we did last time. And what we did last time was we used the translations to determine the new position of our vertex, right? So our new vertex is going to be at -5, 2. Okay, so there's my new vertex at -5, 2. But what the reflection's going to do is instead of points being one away horizontally and then one above vertically, the reflection is going to cause those points that were one away horizontally to now be one below the vertex rather than above. Does that make sense to everybody? Notice that we're using our vertex almost as like our x-axis or our y-axis. So you can move the vertex first as long as then the vertex becomes the things that you're flipping everything around, okay? So again, I'm going to draw this in yellow because this isn't my final answer. But what the reflection would do, if we've already shifted our vertex, it's here. And the reflection wouldn't change any of the distances, but it would change the vertical distances that if they were above my vertex point, they're now below. If things had been below, then they would be above. So that means when I go 1 over, I still go 1 away, but now downward. And when I go 2 over, I still go 4 away, but now downward. Okay? So those would be the points for my parabola if the 3 wasn't there. Right? If all I did was change the vertex and do a reflection, this is where I would draw my parabola. Okay? But I have this vertical stretch that's happening as well. So remember what that's doing. It's taking these vertical distances from your vertex to the points that you're plotting, and it's literally taking the current distance that existed in the parent function and multiplying it by whatever that number is there in that vertical position. So this yellow point right here used to be 1 unit vertically from the vertex. That 1 unit is now getting multiplied by 3, and I am now going to redraw that point so that it is 3 units vertically away from the vertex. So rather than 1 unit below, I need to redraw it so that it's 3 units below. Am I moving it all left or right? No, because this is all vertical stuff. So not 3 units from where it is right now. 3 units below the vertex, right? It used to be 1. Now we're going to switch so it's 1, 2, 3 units below the vertex. And same with this one. This second point here that's 2 away from the vertex horizontally is 4 away from the vertex vertically. Okay, since this is only a vertical change, we're only worried about the vertical distance. The vertical distance was 4. That's getting multiplied by 3, which is going to change that distance to be 12. I'm going to replot these points so that they are 12 units below the vertex rather than 4 units below the vertex. So my points that are 2 over horizontally need to be 12 units below the vertex. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? And same thing for that point that was its mirror image on the other side. Now I have my parabola. And you see that you can do this really slow, right? You can do all the changes one at a time and erase it when you're done and just keep the final one. You could do it very quickly. A lot of you are going to catch on and be like, oh, that means it does this, it does this, it does this. Here's my points. Okay? But we're not all there. And when we start seeing horizontal compressions and stretches, they're going to do the same thing, but rather than multiplying the vertical distance like we've been doing, we're going to multiply the horizontal distances and change where the points are plotted that way. Okay? And you could have a vertical and a horizontal compression or stretch in a problem. Yes? 2, comma, down 6. Uh-huh. Because remember, it's not linear like absolute value. It's not that every time you move over 1, you're moving the same amount of distance you did before. That's why we have to have the parent function memorized. When we go 2 away, we're not just going another 3 down. When we go 2 away, we used to be 4, so now we have to multiply that. So it's like proportions. You got to take what the original proportion was and stretch that out, not use the first one over and over again. Okay? All right, so vertex should be at -5, positive 2. Okay? Axis of symmetry should be at x equals -5. We decided we didn't have a minimum. We actually had a maximum. So it was -5, 2, our vertex point, which meant the maximum value was 2, and that occurs at -5. Okay. What's the domain for our function? John? Good. What is the range for our function? New person. Come on. Yeah, John?
Y is less than -5, less than or equal.
Good. Yeah, so in these functions, we actually reach the point, or not -5, though, 2. The x value is -5. The y value there is 2. So y is less than or equal to 2. Okay, and as far as the transformations from the parent function, we already listed that all right here. Okay?